In this lecture, I want to go through some of the more technical details of NMR spectroscopy before we jump into how to actually use these things to understand the structure of molecules. Okay, so at Ripon, oops, let's get this. At Ripon, we have a 7 Tesla magnet. Okay, now what I want you to take away from the 7 Tesla is that this is a big magnet. All right, it's shielded to a certain extent. So, you know, if you bring something close to it that's magnetic, you have a certain range before it starts to kind of take over and that sort of thing. And really, it's the superconducting magnet isn't the biggest part of the instrument. The majority of the instrument is just something to hold a bunch of cryogens to maintain a superconducting magnet. It can be as strong as 7 Tesla. So anyway, it's just a big magnet. Now, what this does is that this causes, or I could say, with this magnet, the 1H nucleus requires 300 megahertz to flip from the alpha state to the beta state. Okay, so 300 megahertz is kind of the number we want to keep in mind. So let's break this down a little bit. So 300 megahertz is a frequency of light, a frequency of electromagnetic radiation. And apologize, it's a Sunday. My family is living their lives downstairs, if you can hear them. So I don't mind them. But anyway, so it's a frequency of light. Now, megahertz is 10 to the 6th hertz. So mega is just the standard kind of SI prefix. So let's do a little bit of math. I'm actually not going to do too much in front of you, but let's say that we have, if we recall that E equals h nu, where nu is the frequency of light, h is Planck's constant, and E is energy. What's the energy of 300 megahertz light? Okay, and so if we do the math, we get about an energy of equivalent to about 10 to the -6 kcals per mole. That is, if we sort of plug Planck's constant in, we plug in nu is equal to 300 megahertz, and we do the typical unit conversion on that, we get an E equal to 10 to the -6. Now, what this corresponds to is this is the energy difference between alpha and beta, and this is for a particular nucleus. That is the 1H nucleus. Okay, running out of space a bit. I'll have to turn the page here in a second. So one particular nucleus, we can just do this quick math. I mean, the numbers might be cumbersome to work with, so I'll just do the math for you. But recognizing that 300 megahertz is a frequency of light, we see that we get different alpha and beta states. Now, what I'll talk about probably later on is that if you change the magnet, you'll actually change the frequency required for absorption for a particular nucleus. So it was important that I standardized this all by saying I'm using a 7 Tesla magnet. If I doubled the field strength from 7 Tesla to like 14 or 15, I would then have a proportionate increase in the frequency required to flip from the alpha state to the beta state. And we'll go through that later. But anyway, turning the page now, let's look at some other nuclei. So if we have carbon-13, it turns out that that absorbs at 75 megahertz, so substantially less than that of carbon, different, but another number. And this is again for a 7 Tesla magnet. So why a different, why is it a different frequency? The answer is simply that the, if I just keep it simple, the answer is that it's just a different nucleus. So C13 is a different nucleus than the 1H atom, than the 1H nucleus. Probably this would be better if I said has a different nucleus. And by that I mean for carbon 13, it's 6 protons and 7 neutrons, which is different than that of 1H, which is simply 1 proton. So the fact that they're different means we're going to see different frequencies. Now there are ways to sort of get some insight into what to expect, but it's kind of beyond the scope of this class to discuss that. But if we look at other nuclei, you can get a sense of how these things sort of range in their values for the frequency of absorption. So other nuclei would be if we had deuterium, which is the 2H nucleus, even just adding that nucleus substantially change the frequency required to flip from the alpha state to the beta state. Now it's dropping all the way down to 45 megahertz. 19F is a bit closer, and so that's 282. I don't have to draw that so far away. 282 megahertz for 19F. So close to the 1H atom, but not the same. Then there's 35Cl, it turns out, is NMR active at 282 29.4 megahertz. And then 37Cl is 24.5 megahertz. So those are just some examples. Now, what I want to do as an experiment with all of this information is I want to add a bunch of different nuclei to my test tube. Okay, and then acquire some NMR data. This is actually an unusual experiment. Well, I mean, I guess it's a common experiment, but what I'm about to set up will be quite unusual. So what I'm going to do is how are we going to add a bunch of different nuclei to a sample in a test tube? Let's just pick a molecule with hydrogens, carbons. I'm not going to specify the isotope. You'll see why here in a second. Fluorine and chlorine. Okay, so we have a molecule with all of these different nuclei. And again, this is some sort of experiment that we're working on. Okay, so step 2 of the experiment is we're going to add all of this to a giant magnet. Let's turn the page. Okay, let's say it's 7 Tesla. That giant magnet's going to induce a magnetic field, which previously we defined as H0. And as I said, we're going to keep that at 7 Tesla because we are familiar with the numbers. Okay. Then step 3, we're going to shine a spectrum, which is a range in terms of something with frequency and wave properties, a spectrum of radio waves. Okay, so you could think about the spectrum as range if you want to. Just a bunch of photons with different energies So we have a bunch of photons with different energies. And then for those photons with their different energies, they are going to range or ranging within the radio wave frequencies. Okay, so it's not like we're going to shine gamma rays on this thing. We're going to mostly shine radio waves. And don't worry about that technology. It's pretty easy to do that. So let's say it's about 1 to 400 megahertz is the light that we're shining on this system. That would be in the light with those frequencies would be within the radio waves. So we wouldn't really notice them. We wouldn't see them. They have the frequency is too low to be detected by our eyes as color and that sort of thing. Then what we're going to do is after we shine all of this on our tube that's inside of a magnet, we're going to ask a detector, which again, don't worry about that technology. We have many types of technologies can kind of detect what light is present or absent from a system. So we're going to ask a detector what light is missing. And it's not going to detect the missing light. Rather, it's going to detect all of the light that that is not absorbed by the system. So, or all of the light that's present. So the detector is going to detect all the light that's present and feed that into a computer. The computer is then going to say, okay, we know this light went in, which is 1 to 400 megahertz, and we know that some light is missing because the detector only gave us back, it gave us back the vast majority of the light, but there were some missing peaks or some missing frequencies. And then the computer delivers. So this is really a computer with a detector. I mean, I guess we could do this before modern computing technology. So we ask the detector what's missing, and the computer that's hooked up to the detector reports back, and it says, hey, if we have, if I plot a chart where I start from 1, I go from 1 to 400, and then this is the frequency of radiation. Okay, what it's going to report back is it's going to say, oh, well, if we just kind of walk down from 1 to 400, just going along, and it's going to say, okay, if we go to a certain number, about 25, we see some missing values. And it's going to report back a peak for that. 30, 45. I'm going to do terribly just so we all know about getting these to scale. 75. So it looks to be, I don't need the approximate signs, you get it. Probably see what's happening here. We're going to skip down for a while and hit to 282 and 300. Okay. So the computer writes back and it says, hey, okay, so if I look at how much light we expect, okay, and then look at how much light was we actually got, I can tell you what's missing. And so these missing peaks are these missing frequencies are going to be shown as peaks with some sort of intensity. So this is sort of like an inverse plot, I guess. So where a low intensity indicates that all of the light passed through, then a higher intensity actually means that the detector received a lower intensity than what it would have expected. So intensity, or sometimes abundance, but this is just really helpful for the experimentalists to see, because now we could say, oh, there are peaks at 25, 30, 45, 70, 282, and 300. So the experimentalist, or the scientist, says there are peaks, and these peaks correspond to absorption events. for absorption events with frequencies of 25, 30, 45, 75. And I guess the approximate sign is good because it's not like it's 75.0. So maybe I should have kept that. So there's going to be a little bit of variation here, subtly, and we'll get to why that is in a second. Now, what this corresponds to is, did I label these as peak A through? I didn't. Okay, that's okay. So the 25 peak, we could refer to our notes and be reminded that at 25, at 24.5, we're going to see 37 CL. It's actually 24.5. So it's a little bit off. I'm sorry. Let me get this clarified here. 37 CL. Now at 29.4 is where we expect 35 CL. So the fact that we see a peak at 30 tells us we probably have a chlorine atom present. So the combination of these two peaks would tell us we have a chlorine atom present. That's pretty helpful. Okay. Now, if we go to 45, that suggests that we have a hydrogen present as the deuterium isotope. And that is approximately 45 megahertz. 75 tells us that we have carbon, which is indicated by having a carbon-13 isotope present. It's not the most abundant isotope for that carbon atom. The most abundant would be carbon-12, but that's not NMR active, so we don't see a peak for that. Rather, we see a peak for its less abundant isotope, carbon-13. 282 indicates to us that we have a fluorine atom present, and then 300 tells us that we have a 1H atom present. And so we have two combinations of peaks that tell us that we have the same nuclei present. So the fact that we see a peak at 25 and 30 tells us we have a chlorine atom present. If we only had one, maybe that would imply there's something else going on. Similarly, if we have 45 and 300, that tells us we have a hydrogen atom present. And then just looking, 75 tells us we have carbon, and then 282 tells us that we have fluorine. Okay, so we did this. Now, here's the issue. The experiment has indicates that we have chlorine, hydrogen, carbon, fluorine atoms present. Okay. Seems kind of useful, but there's much easier ways to do this. That is, I'm going to say, yikes. Mass spectrometry could have told us this. Okay, all we have are the types of atoms present in the molecule. We don't even have the number of atoms. This is still a long ways away from a structure. Let's look at an example, okay? What would the experiment provide, or what would be the result with propane and benzene? Unequivocally, we could say that these are standard organic molecules, right? Propane, a fundamental hydrocarbon, benzene, which will comprise an entire unit within this class. Okay, so these should be fair game, right? If we're going to determine the structure of organic molecules using NMR, this has got to be able to differentiate between these two. Okay, now if we look, both results would show this. We would see a peak at 45, a peak at 75, and then a peak at 300. 45, 75, and 300. So both of these, even though these are vastly different molecules that are still fair game, would show only these three peaks, because one peak would correspond to the deuteriums that are present in the molecule under some natural abundance, along with the more abundant 1H nucleus, and then the lowly abundant carbon-13 nucleus. We would see the same outcome for both molecules. Okay, well, this is an NMR then is not off to a good start if we're going to use this to determine the structure of any organic molecule. And let me tell you, this is supposed to be a very powerful technique. And so what we need to do is be able to differentiate between some of our standard organic molecules. And so what we need to do is we need to turn to high resolution NMR. So what I would call this low res NMR. All right, let me get a bigger marker here. So low res NMR. But it gets the idea across. We put our stuff into a big magnet, and then we can see the different types of nuclei. Now, what we're going to do with high res, as is the case with any high resolution technique, is we're going to zoom in on those peaks. We're going to go into the peak, for example, at 300, the hydrogen, and then dissect it. And then hydrogen atoms that are subtly different from each other can be distinguished based on what their surroundings are. And so that'll be the focus of the next lecture.